Okay, so now it's my pleasure to introduce the main business of the evening, the Mildner Lecture, and maybe just a few words about Mildner, just a very few words. So he is perhaps best known for his contributions to the improvement in data and communication cables, and which, as much as today, holds immense value. And the company he worked for much of his life, Dow Chemicals company, gave him the opportunity to nominate a recipient for a very large gift. And he nominated our department. And the Dow then head of department, Alex Cullen, introduced this lecture that we have been running since far back as 1972. So that's why we are here today. And this year it is my pleasure to introduce the Mildner speaker, Alan Newby, the Director of Aerospace Technology and Future Programs at Rolls-Royce. So Alan, in his role, is responsible for the formulation of global technology strategy and the delivery of the supporting research and technology programs. And today he's going to talk us about sustainability in aviation. So without further delay, Alan, the stage is yours.
Thank you very much. Right, firstly, thank you very much for the invitation. It's a great honour to be here, particularly as a card-carrying member of the Institution of Mechanical Engineers. So I feel like I'm walking into the lion's den somewhat this evening. However, I'm not going to talk about mechanical engineering too much. I'm going to talk about aerospace. And I'm going to give you a view about what we, and indeed the rest of the industry, is doing to try and improve the carbon footprint of aviation and indeed get to net zero by 2050. So I've included some technical stuff and some general stuff, and hopefully we can have a conversation at the end with some questions if we get time. So let me just make sure I click on the right. I wanted to start with the problem. So you probably hear that people like me and others quoting that actually, if you look at the overall carbon footprint and the impact of aviation, it's actually quite small. If you look at the chart there, this is IEA data. Then on the right-hand side there, the smaller pie, that transport is about 24%, and of that, aviation is about 3%. So it's a relatively small proportion today. It's very visible, but it's also growing. As other sectors decarbonise, aviation is a relatively difficult sector to decarbonise, and so it will tend to grow if we don't do something to work at it. And the kind of slightly complex cartoon on the right-hand side gives you a feel for some of the impacts as well. We tend to focus on CO2, if you like, which is the kind of the global warming that we're aware of. But I think increasingly we are becoming aware and indeed starting to address what we call the non-CO2 impacts of aviation. And that includes oxides of nitrogen, it includes aerosols, it includes contrails in particular. And I'll say a little bit more about that as well, but contrails, you can see the kind of cartoon there. Now, contrails can be good and contrails can be bad. Because if you lay contrails down during the day, then that's a good thing because it stops the sun coming in and heating the planet up. But if you lay contrails down in the night, that's a bad thing because it stops the heat getting out of the planet. So even that isn't a simple bit of science, and there's increasingly a lot of research going on the non-CO2 effects of aviation. And this one just shows you that. You can see that if you look at the CO2 is the big bit that we talk about. This is, if you like, the continuous or the total impact of aviation on the climate. And you see that's 100%. Up here, we understand the greenhouse gas impact of CO2 and indeed oxides of nitrogen. We're pretty clear we understand those now. We understand how they're generated and we understand the impact on the planet, particularly for a long term. But then you get into things like in-flight aviation-induced contrails that can form cirrus clouds, indeed. And there's a significant amount of uncertainty on those. So this year and indeed last year, there's quite a lot of research being launched by NERC, by the Aerospace Technology Institute, sponsored by the Department of Transport, to really get to the bottom of that and understand it. And it particularly forms where you've got saturated air, and we think one of the contributing factors might be the particles in the exhaust of the aircraft, which causes the nucleation. You then get the ice forming, which then can go in certain climatic conditions to turn into contrails as well. So increasingly now we're looking at that, and the impact of that could be as much, if not more, than the pure CO2 itself. So you'll hear more, I think, in the media in general about the work we're doing to try and understand and address the impact of non-CO2 effects. And one of the things we are looking at, they only occur at certain latitudes, at certain altitudes, and in certain climatic conditions. So one of the things we're starting to think about is through clever routing of the aircraft and clever understanding of the weather, can we kind of optimize the flight path to eliminate the production of contrails. And then I wanted to just, again, talk a bit more about the impact of aviation. So The good news is that aviation efficiency has increased by about 11 times since about 1960. However, the bad news is that over the same period, RPKs, which basically is revenue passenger kilometres, the amount of the distance people fly times the number of people, has gone up 75-fold. So in actual fact, aviation emissions have increased 7-fold. So you can see there on the graph that the increasing line there, the black line, that's traffic growth. And on the red there, that's the amount we've done to address that through efficiency improvements and so forth. And we're gradually driving those down. But at the moment, we are being outpaced by the growth. And if you look forward, even post-COVID, the predictions vary. Boeing and Airbus have slightly different numbers. Other people have different ones. But you're looking at something like 3.5% per annum traffic growth, which is, if you work that through, it says that traffic will increase by about 2.5 or 3 times by 2050. So that's the challenge we've got to address. It's the growth that we've got to address as we go forward. Now, I highlighted that number. That's in 2018, so it's slightly out of date. That's 0.125 kilograms of CO2 per revenue passenger kilometre. And just to give you a calibration of that against other modes of transport, and this is some Bayes data that we've got along the bottom there. That's 125, and you can see some of the figures. These are for single occupancy, for a small car there, for a large car, for buses and railways, and medium EV. Now, clearly, EVs depend on how you get your electricity. If you get pure zero-carbon electricity, then that number goes right down. But interestingly enough, I put an air travel number in there, which is, that's an EasyJet number. They've got a relatively modern fleet, and they're doing an awful lot to mitigate the production of CO2 through the way they fly the aircraft and through having modern aircraft as well, and that's gone right down to 70 grams rather. So quite a lot to do. The challenge is growth, and that's what we're trying to address as we go forward. Now, there are very many roadmaps that get the industry to net zero by 2050. This is just one of them, but it gives you an idea of the kind of factors that we're looking at. Now, the kind of component parts vary amongst the different predictions, how the very relative magnitude of them, but the constituent elements are more or less the same. So you can see, if unabated, that's the kind of growth that we were talking about there. You can see the growth there from the 1 there up to the 2.5 to 3 I talked about. And we know that we continue to improve engine technology and we continue to improve aircraft technology, so we will mitigate that in part. The other thing that again, increasingly focusing on is operations. Those of you who fly a lot know that it's very rare that you go direct from your takeoff point to your destination without some kind of diversion, some kind of holding pattern, and particularly in crowded airspace like you've got in Europe. The predictions suggest that up to 10% of CO2 could be reduced just by optimized routing, flying straight around, optimum altitude all the time, optimized routing, and much clear focus on delivering those. One of the complications in Europe is single European skies, which is kind of more political than technical, which we're working through. But equally, the way you fly the aeroplane, even with today's technology, can give you a significant benefit in the reduction of CO2. And then you can see some other things in there. There's the alternative fuels and alternative energies, which I'll talk about a bit more as we go forward. So you've got battery aircraft there, and again, they will be probably more suitable for very short missions, and I'll say more about that later. And then we see in some of these predictions hydrogen beginning to come in, and I'll talk again a bit more about that. And then in the near term, the things that we're beginning to look at are really sustainable aviation fuels, and you can see there HEFA is one of the ones that's most commonly used today. That's basically used oil and fats, and that's the most commonly available one today. There are other biofuels along the way there, and then ultimately power to liquid, where you capture CO2 and you combine that with hydrogen to synthesize an aviation fuel. But you can see among there the demands that we've got as an industry going forward. A big pull on biomass, and again, potentially competing with other sectors for that biomass. But also, many of these roads lead to a significant demand on renewable energy if we're going to address that one, and I'll say a little bit more about that as we go through. But again, if you follow all of those and they deliver on that, then you get through to net zero by 2050. There is a small amount in there for carbon dioxide removal, so that's carbon capture and storage, that kind of thing, which again, we may do. And to me, one of those, if there's one message for today, it's things like carbon capture and storage, or direct air capture as we call it, we should just get on and do. Similarly, the production of hydrogen, whether or not that's going to be used in its native form, burning in a gas turbine or a fuel cell, or indeed used to synthesize fuel, again, we should just get on and do that, and we'll work out some of the other solutions. And you can see that's what, from a technology point of view, we know the routes forward. The challenges to that will be making sure we've got the right amount of resources available to the industry and the political and economic will to get on and do it. And so part of our role isn't just about developing the technology solutions, it's working with governments around the world to say, look, let's have in place the carrots and the stick to incentivize the operations in a zero carbon world. So what are we in Rolls-Royce doing about it? But typically, us and others divide this into three basic component parts. One, it's kind of a bit shorthand, but the best fuel is the fuel you don't use. So what we're trying to do in the first place is continue to improve the engines and the aircraft around us. And despite, relatively modern aircraft and engines, we still see significant opportunity for improvements in the fleet of the aircraft and the engines around us. So that's kind of the first pillar that we will continue to address. Then increasing uptake of sustainable aviation fuel, and we've been doing some work which I'll come on to in a moment, making sure that our engine's 100% compatible with sustainable aviation fuel, so that won't be a barrier to it. Technology won't be the barrier. And then finally, we're also looking at zero carbon solutions such as hydrogen and electrification, and those are the ones that we're working through. And in fact, in many cases, are well advanced in some of our demonstration activities. And what I was going to do during the rest of the talk is just really walk through each of those three pillars. On the first one, I won't go through this in detail, but just to let you know, some of the demonstration activities, there's quite a number of diverse demonstration activities that we've done. So this isn't just theoretical studies of what the potential might be. We're actually developing technologies, and then we can calibrate ourselves on how impactful these will be as we drive towards net zero. So for example, the aircraft on the top left there is one that we flew 2 or 3 years ago, all-electric aircraft where we took the world speed record for electrically powered flight. Now, that wasn't just to get the record. It was proving that we know how to manage the safety of batteries. We know how to integrate a propulsion system into an aircraft. We're also doing things like a turbo generator system for short-haul aircraft, kind of sub-regional ones where you combine a small gas turbine with an electric motor, a jet motor generator. You can do hybrid solutions. And similarly, we've been proving megawatt hybrid, so that's a 2 megawatt generator that you're looking there. We're also doing work on hydrogen, which I'll come on to, and then developing much more advanced engines. And one of the things I will talk about briefly as well is as we make engines more efficient, they want to run at higher temperatures, and therefore we need to run much more advanced materials, and I'll talk a little bit about where we're going on those. So a significant demonstration program right across a whole range of technologies. The one I will focus on very briefly is just to show you what a big gas turbine looks like these days. So this is an engine which we've just run on a test bed in Derby last year. It's the next generation of engine. It's what's called a very high bypass ratio engine. As you can see from the kind of cartoon on the left, engines get more efficient if you move a lot of air very, very slowly rather than a small amount of air very quickly. So that's what propulsive efficiency is, and that's why you've seen engines getting bigger and bigger over the years. This one is a demonstrator. It's got a fan diameter of about 140 inches, which is over 3.5 meters. And you can see a scale from the guy standing there near the fan case on that one. You can see down the left-hand side some of the attributes that we're doing. It's since the first of our sort of Trent family, which is the generation of engine that power the current fleet of wide bodies, we've improved fuel efficiency by around about 25%. Significant reduction in oxides of nitrogen from the combustion process, much quieter, and non-volatile particulates, which, as I said before, we think will have a significant improvement in terms of the reduction in contrail production. And it's capable from day one on running on 100% sustainable aviation fuel. So that's next generation engine, and as I say, we're already running that on our test beds as we speak. Some of the enabling technologies, as these engines get bigger, as the fans get bigger, clearly these large, what we call the low-pressure system components are getting heavier, so we are looking at the advanced use of composites in there, carbon fibre composites to take weight out. One of the things that we've got in the heart of this engine to allow each end of the engine to run at optimum speed is a power gearbox, and that's already run at around about 64 megawatts. It's a significant part of the engine capability. High temperature materials, including ceramic matrix composites, and down the bottom there to ensure that we minimize our environmental footprint, what's called a low NOx, a lean burn combustor. So really investing heavily in technologies for the next generation of engines. And that's what it looks like coming into the test bed. We ran it first ran in April last year, and then ran up to full power later on. We had to build a new test bed for it. This is up in Derby. It wouldn't fit in any of the test beds that we've got on site, so we built a brand new test bed for it, which is an enormous construction. And you can see that's the inside of the test bed with an engine. So that's a 3.5 meter fan on it there, so it gives you a size and scale of the test bed that it runs in. We ran it a bit like, you look at some of the old films of the Apollo days, we actually ran it like that. That's the third line of defense control room. You've got the first line of defense is the guy, the driver, who sits there with the throttle. It's actually a mouse these days, who drives the engine. Then you've got the immediate test support crew, and these are the back office guys doing all the analysis, looking very nervous there as the engine starts up and runs up to full power. And we actually ran that up to 85,000 pounds of thrust. That's the same as you would see on a very large wide-body twin-engine aircraft today. So we've demonstrated that kind of thrust, and we've done significant amount of running so far, and lots of data that we're chewing through at the moment to understand how it performed. But very, very satisfying. This is a program that's been, it's an idea that started in about 2013, 2014. We've gradually taken it through the design process, and now we've got that realization of this engine which deliver these world-leading fuel efficiency and indeed environmental credentials. So that's what we're doing to develop current engines. I also wanted to talk about sustainable aviation fuel, and you can see there isn't just one SAF. When people talk about SAF, you tend to think it's one thing. It's not. They all have to combine to a single formula, if you like, to allow them to be a drop-in solution. But actually, they come from a variety of routes, and I think there's either 8 or 9 pathways cleared today. So you can see today, the one down the middle there, that HEFA, that's hydroprocessed esters and fatty acid. That's what a lot of people run in today. We've done demonstrations using used cooking oil and fat, as I mentioned. You can also use municipal solid waste, convert that ones. Agricultural waste in terms of alcohol to jet, oils, fats and greases, and then algae as well. So we're looking at all of those, and all those pathways are cleared, and we're developing those as we go through. Now, clearly, one of the criteria that us and the rest of the industry do is that none of these feedstocks must compete with land use for either food or for water. So make sure we grow them in areas where other things won't thrive. And we're actually looking at 2 things at the moment. One is a kind of drop-in spec, so you've got the production of these has to be consistent with today's aircraft clearance requirements, if you like, but also what we call JetX, which is a fully synthetic one, which will require a different solution. Today, engines are certified to accommodate up to 50% of this fuel, but we've been doing work to prove that they can be safely run and reliably run on 100% sustainable aviation fuel. And we've done this just gives you an idea of some of the range of testing that we've done. Some of the big engines we've run on testbed. That strange thing there is our own 747, that's our flying testbed. We've run one of the MRTT, the tanker aircraft for defence on that one. But we've also done work looking at, with DLR and other universities, looking at the production of contrails when using either a conventional jet fuel or indeed a synthetic one. We've basically flown the big aeroplane there with a chase plane behind it and sampled the air behind it to see how that changes. We did a transatlantic challenge, which I'll talk about in a minute. I said we'd run the demo. A380s, we've done all the flights there, and I've small modular reactors now. You might say, why the heck is that there? One of the things that we're doing as part of the Rolls-Royce family, we are developing and championing small modular reactors because, as I mentioned before, many of the solutions that get us to a zero carbon future rely on zero carbon power. So we are very much proponents of small modular reactors and working very closely with governments both in the UK and in the rest of the world to get those fully accepted and cleared for more widespread use. But through this testing program here, we've now been able to demonstrate that all our current production engines are compatible with 100% sustainable aviation fuel. So as you'll see in a moment, the challenge isn't technical, it's more about how we can get the availability of that fuel. We've also committed that of the engines that we test on our test beds in Derby, in Bristol and in Berlin, we will use 10% of that fuel will be sustainable. And this was the Transatlantic Challenge. It was a challenge laid down by Grant Shapps when he was Transport Secretary, I think very briefly, amongst his various cabinet roles. And this is a challenge to basically fly across the Atlantic on 100% sustainable aviation fuel. We did it with Virgin Atlantic. It's a Boeing 787 with a Rolls-Royce Trent 1000. We basically, on the 28th of November last year, we flew from Heathrow to JFK. You can see there 7 hours, 19 minutes. And I think the interesting thing was that we had to do some work to clear it to prove it was okay and make sure the fuel was fine. But we simply, on the way back, we just topped it up with normal jet fuel and flew back again. So it's not like you've got to change the aircraft or the engine in any way. We demonstrated that compatibility. So as I said before now, we know what we're going to do, and it's just a matter of ramping up the fuel availability. That picture at the top left there looks very 70s, doesn't it? I hate that one anyway. So one of the challenges, or some of the challenges on SAF, it's expensive. Today, it can be anywhere between 2 and 5 times that of conventional fuel. So a lot of the work you'll see in government at the moment is price equalisation, price stability mechanisms to make sure that the industry pulls it up. And then you've got the chicken and egg that aviation, are the users going to buy it if they think it's going to be more expensive, and are the producers going to produce it if they think they can't sell it because of the cost? So it's like in the early days of renewables, for example, and wind energy. So the government's looking at the mechanisms to incentivise the production of that. And in fact, the UK has got a target of having 5 sustainable aviation fuel factories in production by 2025, which is next year, and 10% SAF usage by 2030. So within the UK and in Europe, there are some quite significant targets for the uptake of sustainable aviation fuel. And you can see on the right there, that's the kind of scalability we need. And it's really the investment in the plant, and we need it's the policy incentives, the carrots and the sticks, to make sure that people do uptake that SAF. But you can see today we're around about the 1% mark, so we've got a long way to go to get to the kind of 60-odd% that we're going to need as part of the journey to net zero by 2050. So kerosene, SAF, of fairly conventional fuels. I put this chart in because it's quite an interesting one to look at in terms of if we're looking at other things, what might we consider? So for an aeroplane, there's 2 criteria. One is how much does a fuel weigh, so the gravimetric density, which is the axis along the bottom there, and the other one is how much space does it take up. For automotive, the gravimetric, the mass isn't such an issue, but volumetric is. But for us, it's both of those. It's how much space does it take and how much does it weigh for a given amount of energy. And you can see one of the things that we and others in the industry have been looking at. This is the grouping we've got today. So these are the kind of hydrocarbons that we use today for automotive, excuse me, and for aerospace as well. I did actually use this chart with a group of the Derby Medical Society. I put the body fat in there. So I feel we could solve the world's energy crisis and obesity crisis all in one go if we could find a way of harvesting body fat, but we're yet to find a way of doing that. And there's some interesting things in it. Down here are batteries. I know you guys are electrical engineers, but we've really got to do better on batteries, and I'll say a bit more about that as we go through. Then you things like LNG, LPG, and down here, and this is why hydrogen gets very, very interesting, because it's about 3 times the energy density by weight, by mass, if you like, compared with kerosene, and that's the interesting benefit, if you like. Having said that, it takes up more space, and you can see, sorry, I went the wrong way. You can see from the little inset there that for an equivalent amount of energy, then hydrogen is significantly lighter. It's about a third of the weight of the equivalent energy in kerosene, but it takes up 4 times the volume. And that's the challenge if you integrate it into aircraft. And you'll see some very interesting design of aircraft to do that. So that's why we are very interested in hydrogen. If you can accommodate the volume, then from a gravimetric point of view, it's very interesting. Other people are looking at things like methanol and for ammonia. Part of our business, look at large-scale reciprocating engines, so we're looking at running some of those on methanol. Liquid ammonia, as you probably know, is nasty stuff if it leaks, but you may see that for use in shipping, particularly on tankers where you've got very few people on board. You want to go long distances, so ammonia might have a place there. So again, the industry is looking hard. On one side, we've got hydrogen, which is a very simple molecule, which is very difficult to handle because you need to keep it very cold. And on the other hand, you've got this complex hydrocarbon, which is expensive to produce and make. We're trying to work out if there's anything in between that might suit the needs of aviation. And one of the things you come back to, so today, the world has been, thus far, the world has been quite simple. We've had kerosene, you deliver it to the aeroplane, you have some kind of infrastructure and you use it in your aeroplane, very straightforward. And if we go down the sustainable aviation fuel, it has got significant advantages because it's a drop-in solution. I'll need new refineries to produce it, but I don't need to change my infrastructure at the airport, and I don't really need to change the engines of the aircraft. It's very much a drop-in solution. Another one is power-to-liquid SAF. That basically allows, if I capture CO2, I've got my source of carbon, then if I combine that with hydrogen, which I've electrolyzed, then I've got a truly synthetic fuel. And again, that will be a drop-in solution. The other thing I could do, if I'm producing hydrogen, I could look at using that hydrogen directly, either through a fuel cell or indeed burning it in a jet engine. That's one of the other things we're looking at. Or, if I go all the way down the bottom here, all electric solutions which don't require any intermediate process if I can make the physics work on the aircraft. So hence my comment earlier that a lot of these solutions, once we've kind of exhausted the supply of bio-derived SAF, then we're going to need significant volumes of zero-carbon electricity to allow and enable all the other pathways to be sustainable. And if you look at what the world is doing today, there is a significant diversity in terms of the number of solutions. So we've got all electric aircraft. There are electric aircraft certified and flying today. That's a Pipistrel trainer up the top left there. And again, that works, relatively small, short-range aircraft, but it's clearly viable. There are many, many people looking at what's called eVTOL or urban air mobility solutions, including Vertical, based in Bristol in the UK, others like Volocopter and Joby and others doing those kind of solutions, relatively short-range, all-electric solutions. Lilium's a slight outlier insofar as most of them are using propeller-type applications, whereas Lilium have decided to go for a jet solution. And you can see it's not all about short-range flying taxis, as they've been called, people looking at 9-seater variants like the one from aviation there, but again, battery electric. When you want to fly a bit further or carry a few more people, then you need to start looking at perhaps hybrid solutions. This is one that Heart are doing, based in Sweden. That started life as an all-electric, but when they wanted to look at the range in the passenger combination, then it ended up becoming a hybrid solution. And then down the bottom here, there's a whole load of hydrogen solutions. And you can, as I mentioned earlier, you can use your hydrogen in two ways. You can either put it into a fuel cell, convert it to electricity, and then use those to drive motors on the wing. And that's what you see there from Zero Avia, based in the UK, and Universal Hydrogen, based in the US. Or, as Airbus are proposing, you can use that in a relatively conventional aeroplane. Instead of storing kerosene in the aircraft, you store hydrogen, and then we've got to work out how the heck you have your gas turbine running on hydrogen, which is one of the programs that we're looking at. So you can see at the moment quite a lot of divergence and diversity in solutions. And I think as the technology begins to mature, then we'll see which of those will really become mainstream as the technology matures and indeed as the markets mature. And one of the challenges we're looking at is we know we're going to need some of these different solutions. This is a forecast looking at various models, because again, there isn't just one model on what the industry will need from a fuel source going forward. So if you look today, 2019 data, Jet A, that's today's jet fuel, if you like, and various suggestions and proposals how that split might look going forward. The International Energy Authority says that it'll be about 23% in 2050, 45% bio-SAF, power to liquid 30%, 2% hydrogen. You can see those vary. But I think the point of showing this is we know bio-SAF isn't the solution. It's not going to fill all the demands of aviation, so we're going to have to do something else. That may be a power to liquid SAF, a fully synthetic SAF, or indeed it may be hydrogen. And now if you've got hydrogen, that's, as I said before, it's your input ingredient for your e-SAF, if you like, or your e-fuel, or indeed you can use it directly in the turbine. And so how do those pan out? We tried to put this together because of all these diversity of opportunities, if you like. What do we think the future will look like for the various competing energy sources and propulsion system solutions? So today, the ubiquitous gas turbine really covers the whole range, right from commuter aircraft all the way through to the large transatlantic and trans-Pacific wide bodies that you fly on today. Now, clearly, if we substitute that for a drop-in solution, then the properties of the fuel are such that it doesn't really make any difference to the operation of the aircraft. But when you start looking at some of these more novel solutions, for example, urban air mobility, then we see that really a relatively short range applications, low numbers of people. And on the charts I showed you earlier, you can, typically 2-4-seaters. You may be able to extend those by a hybrid solution where you take a small gas turbine, combine that with a battery, for example, and gain a bit more range, or indeed, as many others are doing today, looking at fuel cell solution. And they could begin to get into the regional market, so 80, 100-seat type aircraft. That could be a real opportunity for fuel cells. If you want to fly further on a true zero-carbon solution, then you want to put those through a gas turbine, and that will allow you to go well into the narrow-body sector. And there's no fundamental reason why you shouldn't fly long distance on hydrogen, because the longer you go, the more fuel you've got, and the bigger the benefit for a lighter solution. The challenge, therefore, then becomes accommodating the volume on a very, very big aircraft. But nevertheless, we see that as one of the solutions in the long term for longer range, more mass transport solutions. But the bottom line for a company that makes gas turbines primarily, is that we still see that there are significant opportunities for those as we go forward. The challenge will be for us making it basically fuel agnostic, whether it can run on sustainable aviation fuel or indeed on hydrogen, and that's a lot of the work that we're doing. I won't go into lots of detail, but I put this one in just to show you some of the challenges associated with electrification and why it works on small aeroplanes and why it doesn't work on big ones. So we've got there Twin Otter, which flies across some of the Highlands and Islands of Scotland, 320neo, which if you fly anywhere with EasyJet or many other European airlines, that's your typical workhorse, single-aisle, narrow-body aircraft, and then on the right side there, the A380, typically operated by BA, Lufthansa, Virgin, and so forth. And the challenge here is how much of the total weight of the aircraft the fuel makes up. So if you can see for this small aircraft, OEW is the operating empty weight. Then you've got the payload, which is you and me. That's the fare-paying passengers, or it could be freight in this case. But you can see, if you look at that one, of the total weight of the aircraft, fuel's only a relatively small part of that. So if I've got a fuel alternative that weighs a bit more than that one, it's not the end of the world. I can maybe shorten the range or perhaps take 2 or 3 passengers off, but I can still make a viable aircraft because that grey bit there of my fuel is relatively a small proportion of the total aircraft weight. If you look at something like an A320 here, then it's about 1/5 is the total weight of fuel. So it gets more challenging because, I've got the same amount of fuel as I've got on the payload. And the payload are the guys that, that's us, that's the fare-paying passenger, that's where your revenue comes from. So if you start shedding payload, then you begin to question the model of the airline. So you've got to find a way of restoring that. And then if you look like something at a 380, it carries a significant chunk, nearly 40% of the total takeoff weight of that aircraft is on the fuel. So if I've got a fuel system or a fuel energy value, if you like, which is significantly worse than kerosene, then effectively I wipe out my payloads. I either fly very, very short distances, which is unviable for a large aircraft like that, or I basically take the passengers out, so I've got no revenue. So it just gives you a sign of the challenge for more electric aircraft. And again, down the bottom there, we just did some sums just to illustrate that. So an A350-900, that's kind of like the latest modern aircraft, large wide-body twin. So it weighs about typically 280 tons, and of that, about 112 tons of that is fuel. And in cruise, it burns about 7 tons of fuel an hour. If you convert that equivalent energy usage into batteries, it said it would need 250 tons of batteries each hour. So for each hour of that flight, you're using its whole takeoff weight in batteries. And again, that's the challenge. So that's what we're trying to mitigate. So unless there is a significant step change in battery technology, then I think they will be limited to shorter range aircraft. And you see the fundamentals. Kerosene's about 12,000 watt-hours per kilogram, and batteries are about 200 today. That's the 60 challenge. Now, admittedly, electric transmission systems are more efficient than gas turbines, but nevertheless, you've got a factor of 30, which really gets you on par with kind of traditional jet fuel. So that's the challenge the industry is facing from an electrification point of view. So one of the things we're looking at is hydrogen. Does that give you, as I mentioned, it's a very, from a gravimetric point of view, it's a very energy-dense solution, albeit we've got to accommodate the volume. But whereas I said a SAF, a sustainable aviation fuel, is a relatively simple solution because I can drop the fuel into the existing infrastructure at the airport and indeed the existing aircraft and the existing engines. Once you shift to something like hydrogen, then it's a significant challenge. I've got to change the whole infrastructure in the way I produce it, but also in the way I fuel the aircraft and the way I utilize the aircraft as well. So because I showed you the earlier charts about the density of gaseous and liquid hydrogen, the only way that hydrogen is viable for long-range flight is if it's in liquid form. And to get it into liquid form, you've got to store it at minus 253 degrees centigrade. So that's your first challenge, how I handle that. So in terms of the logistics of that, you're not going to pump around the world liquid hydrogen. You're probably going to store it on site. So there you're going to need some way of converting gaseous hydrogen into liquid hydrogen on site and then supply that to either tanks or to the availability by the side of the aircraft there. So from an aircraft point of view, you've got to store it. So you need very, very well thermally insulated tanks on board the aircraft. And then from an engine point of view, we've got to pump it. Again, nobody makes hydrogen pumps today that can pump liquid hydrogen at the kind of flow rates and the pressure ratios and the lives that we need. Yes, you can say people do it in rockets, but they do different flow rates and pressures, but also the life is nothing like you would need for a typical commercial aircraft operation. Then you've got to heat it because it's at these very low temperatures before it goes into the gas turbine. And then you've got to combust it. You've got to demonstrate that you can combust it. And we've been working on this. We've got a whole load of programs. You can see we've done the fundamental analysis. Does it work from an energy point of view? And we've done some early proof of concept work. And then we're developing the technologies, but also doing some integrated system testing. Does it all come together? And we've put in place a program where we're working through those. We've already done a fundamental concept demo. And we've got 3 programs in place. One looking at how you burn it, one on how you handle it, if you like, and how you control it, and the other one, how do I integrate it onto an engine? And then finally, we'll bring all this together on an integrated engine test program. We're doing that through a combination of UK and European programs, both in Germany and in the UK, through Clean Aviation, and also with our partner EasyJet on there. And you can see significant number of university partners and others, including some well-known universities down the bottom here, who are helping us on this journey, because we haven't got all the answers at this, and we need the best and the brightest brains around Europe to help us with that. And so where we've got to on this program, we've done a significant amount of testing already. That strange thing on the top left there, it's a gas turbine. Typically you would find that in a small regional aircraft. It's also the engine that powers the C-130 Hercules, if you've ever seen those of the military transports flying around. We basically converted that to run on hydrogen just to prove that we could. We've also been doing a lot of work looking at how you combust it. This is a test rig in Cologne in Germany, looking at fully representative pressures and temperatures. The one down the bottom there is a rig at Loughborough, where we've been working at how we do the fundamentals of combustion. And what we're going to do by the end of this year, we will have built an engine which will be ready to run on gaseous hydrogen, and we're going to take it out to the NASA Stennis Center next year and run it on gaseous hydrogen. And that strange thing down there is the pump. I said it's one of the biggest challenges. That's ice forming on the outside of the pump there. That's only running on liquid nitrogen at the moment. The plan is to take that further and run on liquid hydrogen, but you see some of the challenges that you face on that one. So a long way to go, but fundamentally we are trying to understand what the various challenges of that systems are. Interestingly enough, the combustion is relatively straightforward. I mean, I guess hydrogen burns, I think we all know that. But you can actually control the oxides of nitrogen and get very, very good and efficient combustion. And I think from our perspective, and indeed the industry, the biggest challenge will be how you store it, how you convey it, and how you control and pump it. I think that's the challenges that the industry will face. So if you bring this all together, finishing off where we got to, if you look at the distribution of flights and fuel around the world, so that darker green line, if you look at the distribution of flights, you can see a significant number of flights today are actually relatively short-range flights. So you can see 90% of global flights are probably less than 3,000 kilometers. But there's this long tail of longer range flights, such that when you look at this from a fuel basis, which is this green line here, then actually, if you're looking there, then there's a significant distribution way out to the right. So the fuel gets burnt on the longer range missions as well. So you can't just focus on the short range missions. And what that means for some of these solutions I've been talking about. So if you look at sustainable aviation fuel, clearly that's a drop-in solution that can cover the whole range of that chart. I can cover the missions right from the very short range up to the very long range missions. Having said that, if I then start to look at some of these alternative ones, for example, these very short range ones. So yes, these electric solutions may be viable and I can do it, but actually they're going to have a very limited applicability in terms of the market and in terms of the number of people and the distance that they will fly. So they'll have a relatively small impact on global CO2 production. If you hybrid that, you'll get a bit more range, so you can begin to eat out a bit more, maybe sort of 10-15% of the global CO2 if you're, I think, fairly optimistic on that one. And then fuel cells, that again, a bit more exciting. If I can fly relatively long range, then perhaps up to 30% of global missions. But to make a real difference, I've actually got to get into the kind of distances flown by your A320, your 737, your typical workhorses that you would see with EasyJet and Ryanair today. And then if you push that out to hydrogen, then we see that being applicable right up to kind of, well, I've drawn the line at about 5,000 kilometers here, but probably further as well. The challenge, as I said earlier, will be on developing the aircraft, making the architecture of the aircraft such that it can accommodate the volumes of hydrogen that require. So that's the challenge we as the industry face. We are looking at these solutions. In the, certainly in the medium terms, we see a significant need for continued use of sustainable aviation fuel, power to liquid, hence the link back to lots of green energy. But we do see emerging opportunities for some of these novel solutions, particularly hydrogen, either in fuel cell form or in direct combustion through a gas turbine. And if you bring that together, just to finish off, from a Rolls-Royce point of view, we're playing in a number of these areas. So, for example, you can see I've been talking here about hydrogen fuel, hybrid electric power, and gas turbines using sustainable aviation fuel. So in an aerospace world, we are contributing right across the patch there. As I mentioned earlier, we're also developing small modular reactors. They will provide the power for some of the energy requirements we've got in the future. We are developing fuel cells primarily for energy purposes initially rather than aviation. And the other thing we're doing is looking at our nuclear capability. We power all the UK fleet of nuclear submarines. We've got a significant amount of nuclear expertise, and we're looking at using that in other areas, either for deployable power. So if you want a remote base somewhere, either for defence operations or for civilian activities, then a small modular reactor or a small micro reactor, I guess, is probably more appropriate. Then we see those as really viable solutions. And the other thing is microreactors for space propulsion. That's something we are working on at the moment. We've got a grant from the UK government to look at microreactors for space propulsion as well. And then just to finish off, given that I am sitting in the electrical and electronic department, we're doing quite a lot of work still on electrical systems because we know a lot of the solutions of the future, be it more electric or fully electric, will require significant amounts of electrical capability, and we're developing those technologies in parallel. And at that point, I will stop and welcome any questions. Thank you.
Colin, thank you for such an insightful talk. And now we have time for questions. Do we have a question ready? Oh, we have a question. Tara?
Is there no R&D being done in like solar power on planes, or is it just way too heavy?
I think there is a little bit done, but again, it's back to the challenge of the weight really and the area. It's not really viable, I don't think. For the amount of power you need, then solar isn't good enough. One of the things solar is a key part of it. It's part of the electricity generation, but in pure aircraft, yes, for very light ones, you've seen, was it Solar Impulse, I think, did that? But I think that's very short range, lightweight aircraft. For bigger aircraft, you're going to need something more energy dense, I'm afraid.
Oliver?
What role do superconducting electric motors play?
I think that's really interesting. As you get into hydrogen, then I think one of the opportunities with hydrogen, as I said, you've got this very, very cold fluid. There's two opportunities. One is that you can develop some more novel thermodynamic cycles because you can use the cooling effect for intercooling, things like that, and quite novel cycles. And the other one is you can make your electrical machines more efficient through the superconductivity. So we see the combination of hydrogen and superconductivity being fundamentally linked. So I think in the future, that's a real opportunity. And in fact, there's a number of people looking at, once you've got the hydrogen on board, combining that with superconductivity and making a long-term solution. Still a reasonable way to go, but you're right, it does fit in nicely when you've got the cryogenic fuels there.
Excellent. We have two more questions here. Yeah.
Do you think there's any place in the mix for lighter-than-air vehicles?
For particular missions, yeah. I think for freight, perhaps, that doesn't need to travel particularly quickly or certain specialist applications, then I think there is. I think it's relatively niche. If you're trying to come at this from a CO2 point of view, then I think relatively limited applications. But for niche applications such as freight and things like that, then we do see that. And there's a number of companies looking at solutions like that. Getting in and out of remote areas, for example, picking up stuff. So we do see that, but not for mainstream usage, we don't think.
I'm curious to know, how do you feel that the UK and Europe are doing on the hydrogen side compared to the US?
Significantly better. So I think it's interesting. So particularly in Europe, there's an awful lot of activity on hydrogen, and we spend a lot of time working through European Horizon programs and so forth. But that's not just for aviation. Right across Europe, there's some big targets on the amount of electrolyzer capacity across the nation and the use of hydrogen for, not just for aviation, but for decarbonising steel production, refining, all sorts of stuff. So it's got a real big push on it, and we see a big pull on that one. In the States, particularly from an aviation point of view, much less, I think. And interestingly enough, we've done quite a lot of work looking at the available land use, if you like. So in Europe, where it's relatively constrained and densely populated, then you simply haven't got the land area for large volumes of sustainable aviation fuel production. Whereas in the States, they've got a lot of land space. So for them, that's a solution. They are doing some work, and through the Inflation Reduction Act put in place by the Biden administration, there is a bit more work on hydrogen, but it's primarily for other industries rather than aviation at the moment. But we see quite a polarized position, which is not ideal if you want to fill your hydrogen aeroplane up in the States and you've flown all the way from Europe. But no, it is a big challenge for us at the moment.
Ben?
I was interested in the modular reactor stuff that you're talking about. And one of the problems with conventional nuclear is it's not great to match with intermittents like solar and wind. Can you comment on how the sort of the modular or the microreactors, are they better in that respect or not?
No, I think we still see them as, providing the base load, if you like. While you've got the intermittency of the other ones, the idea is that they will provide that base load. And I think that's where, for the smaller ones, the microreactors in space and so forth, yes, I think we see those more easy to control. But certainly for the small modular, they're not that small, they're kind of 470, 500 megawatt type ones, so they're relatively large. But we see those as providing the baseload power when the wind doesn't blow and the sun doesn't shine.
Where do you think ultrasonic flights are fitting into your picture?
Hypersonic, or?
Yes, hypersonic.
Yeah, well, not much in civil at the moment. We don't see much of a pull on that. And it's interestingly enough, we did quite a lot of work over many years on supersonic. There is still one company, Boom, for example, are pushing hard on that one, but not many of the mainstream airframers are pushing that. So there may be a niche opportunity for that, particularly for perhaps executive business jets or small ones. But hypersonics, quite a lot of activity through government-funded programs, particularly in the US and in the UK. So either reusable hypersonics or indeed ones that don't come back. So there's quite a lot there, but primarily from a defence perspective.
More questions? Yeah.
I wonder if you can comment on how much more of a gain there could be from getting better sensor data from engines and manipulating that.
I think you're talking single-digit %. But having said that, if you look at a compressor or something, it's probably 92% efficient or something like that. So the amount of loss left is actually quite small. So developing conventional turbo machinery, compressors, turbines, we're on law of diminishing returns. So more we can do on sensing and the operation, particularly off design conditions, we see some real benefits of that one. And it's interesting. When you're designing a new engine, there's always a debate. Do I really need this sensor? Can I put it in? And when you've got a problem, you rely on that sensor to actually help you optimize the engine. So I think it's a long-winded answer saying, yes, we do see that. It's probably small numbers of percentage, but once we've got them there, we've often learned how we can better optimize the engine. Now today, we kind of, with increasingly intelligent health monitoring systems, we can optimize the engine throughout its life cycle. And I think you'll see more of that today. Does you change the operation as it starts to deteriorate, for example? Can you reschedule it in some ways? So I think you will see that. Small gains, but small gains are quite hard these days.
Following up questions?
There was some interest in using electric power for taxiing of aircraft some years ago. I'm not sure if that's ever going anywhere, is it?
There's not so many people pushing it now. The trouble is that you're carrying a lot of weight around with you again. And if you could, the other way of doing it is to have an electric tug, for example. So then you get the benefits of that without carrying it around with you. So there are others still looking at it, but I think from an overall trade point of view, still doesn't look particularly attractive, I don't think. I mean, one of the pilots we talked to said, why would I want to carry my ground support equipment around with me? You know, if you can do it with an electric tug, then you've got a much more efficient solution. Now, clearly, the airlines don't like that because it doesn't give them particularly people like Ryanair who want to be independent from ground handling. But having said that, you know, every pound of weight that you carry has a significant impact on your fuel burn. So at the moment, we don't see any practical solutions. I think others will develop it, and maybe the technology will get better. At the moment, we don't see that going mainstream.
Any more questions?
Kind of just to know what you were talking about compressors, and I guess a lot of that technology that goes into aircraft engines. What are the applications for, you know, with compressors used? I mean, you're doing carbon capture, and I imagine there you're using the sort of same compressor technology for that. But in, say, you know, we see a lot of air source heat pumps, which effectively are using compressors in one form or another. You know, is there opportunities for your kind of technology to push into those areas where traditionally, I guess, you haven't been working in before?
Yeah, I mean, they are quite, the requirements of aviation are quite specific in terms of the design of the pressure of the compressor and the turbines. Having said that, you know, as you said, DAC is about moving large volumes of air. And if you can make a more efficient fan system, then we would do that. And in fact, we have one of our test beds in Derby, we're running a DAC demonstration plant where we've been involved in the design of that system. So we are looking at broader applications of that, yeah. And then, of course, you can go into industrial power gen as well, which are similar ones. But yeah, we're always looking for that. And I think you mentioned as well, thermal management is an area, most areas of sustainability now, you know, whether it be fuel cells or anything else, thermal management becomes a big part of that, and that's a generic capability which we're looking to use elsewhere.
So moving from a historical single fuel solution to a very diverse potential options, do you expect then airports to have infrastructure for all possible short, medium, long term? And is this a problem?
It is, yeah. I mean, that's the challenge. That's the real challenge that the industry is wrestling with now, because if you look at the whole capital investment side of it, yes, I can look at it from the economic side of it, from the efficiency, and I think that's one of the challenges. So I think Bristol Airport has done a lot of work looking at how you would do that. But you're right, I mean, that's why SAF is attractive, because I can just do it in the existing infrastructure. But yeah, there's a massive capital investment required, not only for the on-airport stuff, but as I mentioned before, how does the hydrogen come in? You know, do I actually electrolyse off the airport somewhere and pump in gaseous hydrogen and then do it? So it's a big challenge for the industry. So whilst we can probably have a go at solving the technical problems on the engine, there's an enormous bill required for the capital that goes with that as well. And that's part of what the government's launched a hydrogen task force, and that's part of working through that to see what that bill would be. But it's a massive challenge.
Time for a few more questions.
So we touched on the economics of SAF being 2 to 5x conventional fuel. And forgive me for not asking an engineering question, but what is the scale of investment needed, do you think, to push it down to an acceptable level? And what is your bet on what the price difference will be, the minimum price difference will be for the government to then step in and try and equalize the price?
I mean, I can't give you a number off the top of my head for the capex, but I think once you start to scale up, then, you know, the number I showed was 2x to 5x. I think it'd be nearer the 2x. But then I think, but what you've got to pay is that today, as we probably know, aviation fuel is untaxed. So you've got that baseline. If you start putting a carbon tax on that, then the price differential becomes a lot different. So I think, yeah, maybe 2x is a number that we will get towards. And then the government is looking at how you solve that equation. But again, it's an unfair comparison if you look at untaxed kerosene against a SAF solution. And I think that's where you'll see it. If your carbon starts to cost you more, then the SAFs will become more attractive. And that's what the government's working through.
Just to follow up on the economic, I guess, appetite is, do you know off the top of your head how much money is spent on kerosene per annum in the UK?
No, I don't.
Just to figure out how much.
No, I think we'll get the numbers somewhere, but it's a significant amount of money. I mean, the UK is, it's, I think only about 6% is domestic, is a lot of international fuel. So we do a lot of long haul stuff from the UK as well. A significant bill. And it's an interesting one because that bill isn't just for UK flight, if you like. It's, it's transatlantic and trans-Pacific, well, not trans-Pacific, but transatlantic flights as well.
One more question? If no one will, I will. Oh.
This is a rather light-hearted question, but for short-haul flights where a substantial part of the energy is in takeoff and getting to altitude, and if you want to do that electric but keep all the infrastructure on the ground, there's a well-known solution from gliders, which is to cable launch the aircraft. What do you reckon?
Yeah, what do I reckon on that one? Yeah, I think I'd stick to gliders on that one, I think, really. I think, and the challenge as well, particularly if you've got a, it depends how good, you need good aerodynamics on that as well, because obviously one of the interesting challenges, I'm going to ask the question you didn't quite answer, but it gives me an opportunity to say something else. If you look on electric aircraft today, yes, there's the mission fuel, whether it be, let's say it's 100 kilometers or something like that. One of the challenges that you face is your reserves fuel. So if you're up in the Highlands and Isles of Scotland and the mist comes down or something like that, you've got to have that alternative energy source. So you're actually carrying even more weight in batteries, which allows you to get to a diversionary airport. So that's the challenge, is having energy on board that if things don't come to plan, so you can go around and go off somewhere else. And one of the reasons people look at hybrid solutions is that you could do the majority of your flying on electrification or electricity, if you like, but if you then need to go somewhere else, you can kick in with your reserves, which are in kerosene. So you don't necessarily need to use your kerosene, but you've got something which is probably 30 times more energy dense, so you're not carrying around that weight, or that mass, if you like, for those occasions when you don't use it. So, yeah, maybe you should patent it, I don't know.
Okay, so that concludes the Q&A, and I'll pass the... And we'd like to thank our speaker again.